So we're going to talk about three things. I'm going to talk about the science of climate change, I'm going to talk about emission scenarios, and I'm going to talk about options for emission reduction. So those are the technical options. And the reason that I start with the science of climate change is, well, this is an economics class, right? So why are we talking about physics and chemistry and a bit of biology? Two reasons. One, if you want to solve a problem, you better understand the problem, right? That is your starting point. If you want to have a workable solution, you better know what you're trying to solve. Second, even though all of you have no doubt read and heard about climate change and the science of climate change, unfortunately, you can find any amount of nonsense on the internet. And not just on the internet, you can also find any amount of nonsense in the so-called quality sources, like the BBC or the Guardian or things like that. CNN, they regularly talk complete shite if it comes to the science of climate change. So just to put it all on the same page. And I mean, it ranges from the amount of nonsense that you can read on the internet, from Earth is going to explode because of climate change, and there is a paper in an academic journal that indeed makes this claim. That's not going to happen. All the way up to it's a Chinese hoax, right? By the current occupant of the White House. That's also complete nonsense. There are some conspiracies, there is some exaggeration, but the Chinese had absolutely nothing to do with it, right? If anything, it's more American companies rather than the Chinese government that is behind some of the disinformation you see about climate change. Or NGOs like Greenpeace, right? So, let's start with the science of climate change. What you're looking at is 9 graphs. On your left, you're looking at observations and reconstructions of the atmospheric concentration of the 3 most important greenhouse gases from top to bottom. That is carbon dioxide, CO2, methane, that's CH4, and nitrous oxide, N2O. And then in the sort of the large figures, you're looking at the concentration since the start of the agricultural revolution. It's about 10,000, 12,000 years ago. And in the smaller insets, you're looking at the same thing since the start of the industrial revolution, say 200 years or so ago. And what you see is that throughout most of the period of human civilization, right? Civilization is when agriculture started. These concentrations were fairly constant, and then towards the end of the period they skyrocket. That is a graphical illusion. If you look at the smaller insets, then you actually see that they only rose exponentially, right, since the start of the Industrial Revolution. And then on the right-hand side, you're looking at indicators of climate change. At the top, the change in the global mean surface air temperature over the last 150 years. Then in the middle, sea level, you see that has gone up too. And then at the bottom, you're looking at snow cover on the northern hemisphere, which has gone down. Now, these pictures are perfectly consistent with each other. Why is that? There is such a thing as the greenhouse effect, first described by Fourier in 1827. Fourier is the same guy as who came up with a transform. And he did experiments on CO2. And what he found is roughly what is described here. So the sun sends out radiation in the visible part of the spectrum, right? The sun gives light as well as heat. Most of that energy ends up in outer space, right? But the small part of it hits planet Earth. Some of it is reflected at the top of the atmosphere. Some of the energy is reflected by the surface of the planet, and some of it is absorbed by the planet, right? Now, that cannot be in equilibrium, right? If the planet just absorbs heat, and that has been going on for a couple of billion years, then we would have evaporated a long, long time ago, right? So there must be another process going on to keep things in equilibrium. And you have noticed probably that the Earth doesn't light up at night, right? If it does, you smoke too much. But Earth does emit radiation in the infrared part of the spectrum. And that goes into outer space. And that is where greenhouse gases come into play. So by definition, a greenhouse gas is transparent to visible light. That is, if the sun hits a CO2 molecule, a ray of solar light hits a CO2 molecule, it just passes right through. But greenhouse gases are opaque to infrared radiation. That is, if infrared radiation hits a CO2 molecule, it absorbs that energy. Now again, that cannot be an equilibrium situation, because all CO2 would have evaporated a long time ago. So a little bit later, that CO2 molecule that is now excited re-emits that energy again in the infrared part of the spectrum. The sky doesn't light up either at night. And the crux of this story is that infrared radiation that is emitted by that CO2 molecule or CH4 molecule, and so on and so forth, is emitted in any direction. So part of that energy comes back to us, living on the surface of the planet, right? That means that on balance, it is, because there are greenhouse gases in the atmosphere, it is harder for energy to leave the planet than to enter the planet. And that means that on balance, it is more energetic, that is warmer, right? And without greenhouse gases in the atmosphere, the average temperature of the planet would not be the 15 degrees that we have now, but rather minus 15 degrees. It would be 30 degrees cooler without the natural greenhouse effect. Now, what have we been doing since the start of the Industrial Revolution? We've been pumping more and more of these greenhouse gases into the atmosphere. And as a result, we've seen it get warmer. At the top graph, the land surface, the graph directly under it, the sea surface temperatures, that is the temperature of the water. The third graph there, the water, the air over the oceans has gone up, sea level has gone up, told you that already. Arctic sea ice, at the bottom graph in the middle, has gone down. We also see that actually further up in the atmosphere, that's the little graph at the top, temperatures have gone up, the amount of energy that is stored in the ocean has gone up, humidity has gone up as well, that's the third graph to your right. That is, if water gets warmer, if the air gets warmer, it can contain more water vapor, right? And we've seen measurements of humidity go up as well, so all perfectly consistent. There is an immediate complication here, and that is that water vapor is also a greenhouse gas. So because it gets warmer, there's more water vapor in the air, and because there's more water vapor in the air, it gets warmer still, right? So that's a positive feedback that you see going on there. And then the two small graphs at the bottom, you see that the glacier mass balance goes down, but also the snow cover is going down. And that is another feedback effect. Because snow is white or grayish, and that means it reflects a lot of sunlight. But if the snow melts, then the surface becomes darker and it starts absorbing more energy, right? That's the same effect as are you wearing white clothes, light clothes or dark clothes in summer, and how hot do you get, right? The same is true for the surface of the planet. So I've given you now sort of the very basic story, right? More greenhouse gases in the atmosphere means it's warmer. That's the first order effect. But I also immediately started talking about feedback effects, right? The water vapor is an important feedback effect. The albedo, the reflexivity of the Earth's surface, is another important feedback effect. And there's all sorts of other things going on in the atmosphere and the ocean that sort of make that very simple Fourier-Tyndall story, more greenhouse gases means warmer. It's just not true. It's just not the complete story. There's all sorts of feedback effects going on in the Earth system that amplify this original signal, and some of them dampen the original signal, right? So what people have done is built enormously complex climate models. They are the second most complex models known to humankind, right? The most complex ones are protein folding models, but these are the second most complex models. And whenever you build a complex model, the question is, do we trust these models? Because you cannot solve them with pen and paper, and they've become almost black boxes, right? So here you're looking at a, I think, too busy picture, but it's the most recent one on this topic by the Intergovernmental Panel on Climate Change. And what you're looking at is a whole bunch of graphs. This one we've seen before, right? The black line here is the observation of the global mean surface air temperature. And what you see is that goes up. Now, those of you who have sharp enough eyes, there's two bands around it, right? The pink, what people have done is they've taken their climate models and they started the climate model to run in the year 1900 and included everything that we assume affects or we believe affects the climate. Everything was put in, and then we traced what the evolution of the climate would be during the 20th century and the first 10 years of this century, right? That's what people have done. And then what you get is the pink range. And it is a range because there's about 30 different climate models that can do this. And what you see is that if we believe that greenhouse gases and aerosols and all those things and volcanoes and changes in solar activity affect the climate, then these models perform reasonably well, right? The observation is bang in the middle of the range. So that is one thing you learn from this. And that is not just true for the global mean temperature. It's also true for the land surface, the graph to the left of it, and for the ocean, the graph to the right of it, and for all the individual continents, and for all the individual ocean basins, right? That's all the little graphs at the top where you can sort of like deduce from the world map what the graph is about, right? So that is what the pink and the black mean. And then they did a second set of experiments with the same 30 or so models, where they started in the year 1900 and ran the climate of the 20th century, but now without greenhouse gases. And then you get the blue range. And what you see is that the blue and the pink separate, right? And what you also see is that the black line, in order to explain the observations without greenhouse gases, actually it's very difficult, right? No model would spontaneously do this. Whereas if you do believe that greenhouse gases affect climate, then it's actually perfectly normal what we have observed. It's just as expected what we have observed. Normal is perhaps not the right word. Now, this is not a statistical proof, right? The range that you're looking at is a range of best guesses rather than a true uncertainty range. But it does seem to suggest, yes, climate has changed, climate has warmed. There's very little dispute about that. And it's very hard to explain this without greenhouse gases, right? Now, we have built some confidence in these models, right? Because they are able to reproduce the last century. So we can also start running these models forward. And then what you see is that by the end of this century, the world may be warmer between 2 and 6 degrees or so. So the pink range that you're looking at is the range of uncertainty around these models, and then different colored lines are different ways in which the future may unfold in terms of emissions, and I'll come back to that. So 2 to 6 degrees warming by the end of the century, and then by the end of the 23rd century, yes, it may get up to 12 degrees warmer, right, or hotter still. So that is sort of the range of projections that we can think about. Now, you may think that the year 2100 is far, far away, but chances are that a good few of you will see the year 2100, right? I won't be around, but chances are that you will be. Why does this surprise people every time? Come on. What do you think medical technology is doing? Now, this is the global mean surface air temperature. The global mean is not particularly interesting. What you're looking at here are maps of future warming. If you go to the right, you see more CO2 in the atmosphere. Oh no, you're moving further out in time. That's 2065, 2100, 2200. If you're moving from top to bottom, you see more and more CO2 in the air at that particular time. Lo and behold, if you put more CO2 in the air, it gets warmer still, right? And if you move further out in time, it gets warmer, right? So that is no surprise. You also see very distinct regional patterns, right? And I'd like to draw attention to two. One, warming is faster towards the poles than towards the equator. And second, warming is much faster over land than over the ocean. And that has to do with the difference in heat capacity, right? And of course, land is where most people live, right? So the global mean is actually mostly ocean and does not affect you and me unless you want to become a mariner, right? So this is the temperature. Temperature is relatively simple. We do not necessarily know the magnitude of the change, the magnitude of the warming, but we do know the sign. It's getting warmer. This particular set of maps has the change in precipitation. It's, again, if you move from left to right, you're moving further out into the future. But now if you move from top to bottom, you actually start in the northern winter, spring, summer, fall, right? That's what you're looking at. And these maps tell you all sorts of interesting things. In the blue, things get wetter, but in the brown, things get drier. So even though the atmosphere can contain more water vapor, that does not mean that it's going to rain more everywhere, right? Because I also showed you the temperature map, and that's not uniform, and that means that pressure patterns will be different, and therefore wind patterns will be different, and that means that rainfall patterns will be different in the future. So even though it will on average perhaps rain more, that does not mean that it will rain more everywhere, right? You also see large areas of brown where it actually gets drier. Another thing that you may notice if you have sharp eyes, that is if you look at our part of the world, in winter it is blue and in summer it is brown. So that there's people who go on telly and say, because of climate change we will have more droughts and more floods. And then you immediately have some sort of wise ass saying, what an idiot. How can it get wetter and drier at the same time? Well, that's not the forecast, right? The forecast for a place like the Netherlands, or actually for most of northwestern Europe, is that it will get wetter in winter and drier in summer. And if you live where I live in the southeast of England, we have a flood problem in winter already, and we have a drought problem in summer already, and because of climate change both will get worse, right? And this is perfectly consistent, right? Of course it's not going to get wetter and drier at the same time, but it can be at different times in the year, right? And that is what you need to worry about. Another thing that you may have noticed from these graphs is that the rain seems to be pushed towards the poles. Now that is not so much an issue on the northern hemisphere, where there's a lot of land to the north of us, but if you focus on sub-Saharan Africa, then the rains that are currently falling, or southern Africa, sorry, the rains that are currently falling over southern Africa will in the future fall over the Southern Ocean. And they're no good to humans, right? They're no good, those rains are no good to agriculture, right? talked a little bit of, I mentioned sea level rise, but I did not talk about it much. If the atmosphere warms, then the ocean must warm, right? Because they're in direct contact with each other. Now, if water warms, it expands. And you may think, why is he talking about this? Because water does not visibly expand if it gets warmer, nor does if you have a cup of tea that's almost 100 degrees when you start, and you let it cool down to room temperature or to drinkable temperature, then it has not visibly shrunk, right? So how can a few degrees of warming of water, of ocean water, be a reason for concern? Well, your cup of tea does shrink if you let it cool down, by only a little bit, right? You can't see it. Similarly, if the ocean temperature, if the ocean water warms, it expands by only a little bit. The problem is that on average the ocean is 3 kilometers deep. So a tiny little expansion of a 3 kilometer column of water, if it's only 0.1%, that's 3 meters, right? Which is around there, right? So it is a tiny expansion from the water's perspective and from the ocean's perspective, but it is a large expansion from a human perspective, right? And then on top of that, of course, we also have ice melting, but definitely for the current century, it's actually the expansion of water, of ocean water, that is most of our concern, right? These patterns are not uniform over space. Won't have time to get into that. Besides temperature and rainfall, there's other things going on. The thing that you would read a lot about is what would happen to storms. And there's good news and there's bad news. The good news is that the area where you would find tropical storms will probably not change. It's not that we will have hurricanes in the Netherlands. Another bit of good news is that the frequency of storms will stay constant or may slightly fall. The bad news is that the intensity of storms, both in the tropics and outside the tropics, will increase. So the wind speed will go up. And that is particularly problematic because the damage that storms do are roughly proportional to the number of storms, or maybe less than proportional to the number of storms, because if a second storm hits you, a lot of the damage that was done in the first storm can't be damaged again in the second storm, right? If your house is blown over in the first storm, it won't be blown over again because it's not there anymore, right? So the storm damage is actually less than proportional to the number of storms. But the force that the wind exerts on your house is the wind speed to the power 3. So a small increase in the intensity of the storm, a small increase in the wind speed, leads to a large increase in the damage that is done, right? So the bad news is actually much worse than the good news is good, right, about storms. I talked about rainfall. The thing that we should not forget is ocean acidification. It's a bit of a separate problem, but with the same cause. If there's more CO2 in the atmosphere, then by the laws of partial pressure, there must be more CO2 in any water body that is in direct contact with that atmosphere, including the ocean. Now, the proper English name for CO2 or carbon dioxide is carbonic acid. And the proper name for CO2 in Dutch is koolzuur. Or if you're German, it's Kohlensäure. Right? I won't do it in French because I don't know. But the crucial bit here is the acid, the zuur, the sour, right? So CO2 is, if dissolved in water, is a mild acid. Now, what do you care, right? You don't. What does acid do? Acid destroys calcium. And you don't care. Your body is partly made of calcium, but we're smart enough to have our skeleton on the inside. So you can safely swim in acidic, mildly acidic water. If you're a mollusk or something, or a lobster, then you have your skeleton on the outside. And you do get damaged by more acidic water. Or if you're a coral reef, you get damaged by this, right? And it's not just sort of the big and visible parts of the ocean ecosystem, but also a lot of the plankton has essentially outer skeletons. And that is basically the basis for the food web, definitely in the ocean, but also in everything that connects to the ocean. And this is a problem that is not fully understood, how big it is and how serious it is and how quickly it will go, but it is not something that we should forget about. Okay, so that is roughly the science of climate change. So where do these greenhouse gases come from? Now, some of it you know, right? Most of the CO2 that we put in the atmosphere comes from the combustion of fossil fuels, right? So what we do is we take a carbohydrate, something that has a lot of carbon atoms and a lot of hydrogen atoms. We add energy and we add oxygen to this, and then that energy breaks the chemical bonds, and that takes energy. But then the C reacts with the oxygen that we added and becomes CO2, and the H that we broke off from the carbohydrate reacts with the oxygen and becomes H2O, right? And it's the formation of those new chemical bonds that delivers energy, and that is why we burn fossil fuels, right? And this is intrinsic to the process, right? You can't get the energy out of your coal or your gas or your oil without oxidizing it and without turning it into CO2 and H2O. Right? This is intrinsic to the chemical, physical process. That's where most of the CO2 comes from. A good bit also comes from land use change. So what we've done is we chop down trees, or we burn down trees and replace them with grassland. Now trees are big and grass is typically much smaller. Both are carbohydrates, but the difference in mass has to end up somewhere, and a lot of it has ended up as CO2 in the atmosphere, right? And then if you make cement, and this is only 2 or 3% of CO2 emissions, you essentially take limestone, and then in a chemical process you drive out the excess carbon from the limestone to make cement. And again, you get rid of the extra carbon by oxidizing it and then venting it into the atmosphere. So that carbon dioxide is the most important greenhouse gas. The second most important greenhouse gas is methane. Methane has 4 main sources. The first of them is cattle or ruminants. So what do cattle do? They eat grass and they turn it into milk and meat, right? If you do the chemical balance of those, then you would notice that meat and milk have less hydrogen than the grass had originally. So what happened to that excess hydrogen? You can't keep it in the cow, right? So hydrogen is dangerous. If hydrogen gets in contact with oxygen, it becomes a hydrogen radical, it destroys everything. If there's no oxygen around, it turns into hydrogen gas, and then you have not a cow but a zeppelin. So that is not good. So what have cows done? A long time ago, they formed a symbiotic relationship with methanogenic bacteria. And what do those bacteria in their tummies do? Essentially, they sacrifice one useful carbon atom and bind 4 harmful hydrogen atoms into CH4 and then burp it out, right? That's what they do. If you want to get rid of this, you may wonder what other animal fulfills a similar ecological role. Well, the kangaroo does, and the kangaroo doesn't turn out CH4, but instead poops out acetone. which also contains a lot of hydrogen. But that immediately tells you what you need to do to a cow to get rid of the CH4, right? You need to genetically engineer it so that its metabolism becomes that of a kangaroo. So this is again a hard problem to crack, right? A very hard problem to crack. Paddy rice is the wet rice, right? So if you have organic material that decomposes in an oxygen-rich environment, it turns into CO2. If you have organic material that decomposes in an oxygen-poor environment, it goes to CH4. And that is what wet rice does. The leaves of the rice plant end up underwater, start rotting underwater, but there's no oxygen there, not enough oxygen there. So it turns into CH4, into methane. And similarly, organic waste that ends up in landfill, there's very little oxygen there, so it turns into CH4, right? Now methane is a peculiar thing. It's methane and its chemical name is, or chemical description is CH4, but it also goes by another name, namely natural gas. And for some reason, natural gas is what we call CH4 when it's useful, and methane is what we call it when it's not useful. But it's the same thing. So whenever you're mining gas or transporting gas in a pipeline that is not fully sealed, you're leaking CH4, right? Or if you're mining coal, often is found together with gas, or you're pumping oil, often found together with gas, you're also leaking a lot of methane into the atmosphere, right? And then there's nitrous oxide, the third most important greenhouse gas, which is mostly from the over-application of fertilizers. That's its main source. And then there's other, much smaller greenhouse gases that I won't have time now to talk about, but they're mostly very specific purposes. So that is roughly where this stuff comes from. And if you now wonder what explains the trends in CO2 emissions, why have these gone up, you can deploy the so-called chi identity. And the reason that you want to understand past trends is twofold. You may just be curious and want to know where it is coming from, but also we want to project into the future. We want to know where is this problem heading to, and then it actually helps if you have a decent understanding of the past, because that is typically your guide to an understanding of the future. What you're looking at here, the equation that you see is the so-called chi identity, and it's an identity, right? What it says is that emissions E equal the number of people P times per capita income Y over P times the energy intensity of the economy X over Y times the carbon intensity of the energy system E over X. And this is true, right? Because P cancels against P, Y against Y, and X against X. So really this says E is E. And you can't disagree with that, right? And that's why it's an identity. It's also useful. So in the in the black line even, you're looking at the change in carbon dioxide emissions over the last 45 years or so. And what you see is that over that period, emissions have roughly doubled. These are emissions from fossil fuel combustion only. And you may ask yourself, why? And the chi identity actually helps you to decompose this particular trend. And the first thing that you want to do is look at the population. That's the dotted red line, and what you see is that the number of people has roughly doubled over the same period, slightly less. CO2 is slightly doubled and slightly more than doubled, population slightly less than doubled. So you immediately learn that CO2 per capita has gone up, but only by a little bit, right? Then if you look at per capita income, that's the blue line, that has doubled over the period. This is per capita, so if population doubles, per capita income doubles. then of course the size of the economy has quadrupled over this period, roughly, right? Now the size of the economy has quadrupled, but CO2 has only doubled. So something good must have happened as well. And that is the other two lines that you see in the purple, I think it is. You're looking at the energy intensity of the economy. So essentially, how much energy should we put in to make a euro, right, in terms of value added. And what you see is that energy intensity is roughly halved over this 45-year period. Whereas the green line, that is the carbon intensity, how much CO2 do you emit per joule of useful energy, you see that has stayed roughly constant. It's sort of increased a little bit, then it fell, essentially as people switched from coal to gas, and then it started rising again as particularly China and India started growing rapidly and burned a lot of additional coal. But it has stayed roughly constant, right? So we now have a rough understanding of where this comes from, right? So the economy has grown, CO2 has not grown out nearly as fast, and this is mostly because we have become more efficient in our energy use. Not because we put up solar panels and wind turbines. No, the main driver for the relative fall in CO2 emissions relative to what they could have been is due to efficiency improvements. So now that we have a reasonable understanding of the past, we can start kicking this into the future, right? And that is what you see here. This is another projection of how warm it might become during your lifetime. The areas that you see is the uncertainty about the climate models and the carbon cycle models, and the different colored lines are different ways in which the future may unfold in terms of population and emissions and so on and so forth, right? And typically these studies follow the Kaya identity that I just gave you, and here we're looking at Yotsi Kaya, who is nowadays at Tokyo University. Some of you laughed when I sort of said, yeah, this must be true, right? And it's essentially trivial what Kaya did there, and it took him 10 years to write it up. The Kaya identity was famous long before the article was published because Kaya himself thought it was a trivial thing to say, right? But trivial things sometimes are the best thing to realize. Now, the graph that I showed you is about CO2 emissions, right? And if you want to project CO2 emissions, what do you need to do? You need to know how many people there will be in the future, how rich they will be, how much energy they will use, and what sort of energy they will use, right? And that is a tough problem, right? And even population, which we often think of as relatively simple because there's so much momentum in population, that is, you guys will have babies in 10, 15 years time, right? That's pretty predictable on a population scale. I won't predict it for every individual of you, but those things are relatively predictable, right? I wasn't talking about her specifically. But actually, if you move further into the future, predicting population growth is actually a much tougher problem than most people realize. And then you need to predict economic growth. Hard. You need to predict consumption patterns. Stuff, right? But then it's not just that you need to do this for CO2 from fossil fuels. If you want to predict future methane, you need to know how many people there will be and how rich they will be and how much meat they will eat, right? And so on and so forth, right? So this is, and you need to know how farmers will farm into the future if you want to project nitrous oxide emissions. So this is a tough problem, and some brave people, or some would say foolish people, have tried to do that. And here you're looking at some of the projections that people have made and broken down in the chi identity. So top left, you're looking at population growth, and sort of the middle scenario there says that the world population will stabilize at around 10 billion people. The top scenario says it may go up to 14 billion people. And the bottom scenarios say, well, it will peak at 8.5 and start falling towards 7.5 by the end of the century. And that's a wide range of results. And the big difference between the two scenarios are the projections of the speed at which fertility falls. Then the next graph, top right, you're looking at income. You see again a wide range, right? You also see that actually, if you look at the most pessimistic scenario, currently the income, average income is around $7,000 per person per year. The most pessimistic projection brings this up to 20,000, right? Which is Portugal. It's good, right? That's a very decent standard of living. The most optimistic scenario puts it, or the highest scenario puts it at 140,000. People in Luxembourg aren't that rich now, right? It's very difficult to imagine what the world would be like if the average income would be $140,000 per person per year, right? Yeah, this is real. This is real. This is not inflation. Then again, if you sort of like think back 100 years, people were dreadfully poor then, right? And they could not even imagine the life that we have now. So is this overly optimistic? I think it's a tad over optimistic, but that scenario is definitely out there. The reason that the most pessimistic scenario is still fairly optimistic, right? Almost a tripling of average income, is that these are scenarios that come out of the United Nations, and they have been approved by every government in the world. And you can't get government approval if you say, well, we're going to wreck the economy, right? Because every government, apart from my government, at least pretends to stimulate economic growth, right? Doesn't necessarily succeed, but that's what they try to do, apart from. Anyway. Energy intensity is the next one. Again, a wide range of results. The good thing about energy intensity is that those projections are roughly in line with sort of the first 40 years that you see, where we have seen this drop in energy intensity, and the models project that it will continue into the future. If you look at the final graph, you see a mixed picture, but most scenarios sort of project that we will turn away from coal towards gas and then towards renewables. And that is a scenario that is baked in there that is not entirely in line with what we have observed, right? I mean, for the last 45 years, this trend has been flat, but the projections are by and large that it will go negative. That is, and carbon intensity will fall, that is, we will emit less CO2 per joule used. Go ahead.
Yes, is that fall in energy intensity taken, like predicting governments to try to motivate?
No. This is without policy, without climate policy. So this is the basis for a lot of the future projections that you see out there, right? So if somebody says the world will warm by 2 to 4 degrees, or by 2 to 6 degrees, during this century. It's these sort of things that are behind it, right? Because if we stop emitting CO2 altogether, then in this particular graph we end up at the brownish yellowish line, right? That is, if we just do what Greta Thunberg says and stop emitting CO2, then we end up in that line. So the projections of future warming have baked into them projections of future population growth and energy use and so on and so forth, right? With all the uncertainties that come with that. Before the break, I introduced the Chi identity, which is given here again. Now, if the top line is true, then the bottom line is true as well, right? So if we take the log on both sides of the equation, then it's still the same thing, right? And then if we take the first partial derivative to time on both sides of the equation, it's still the same thing, right? You may not be used to this particular notation, dl and e dt. What is that, right? But dl and e dt is of course 1 over e times e dt, right, by the chain rule. And the e dt is just a change in e, so that's typically denoted with an e and a dot above it. So dl and dt is just a proportional growth rate, right? That's how much emissions change per year in percentage. Now, what does the change version of the Chi identity tell us? That the change in emissions is equal to the change in population plus the change in per capita income plus the change in energy intensity plus the change in carbon intensity. And then immediately tells you that if you want to reduce emissions, and that's the purpose of climate policy, you have 4 basic things that you can do. And the first thing you can do is reduce the number of people. Now, that is typically not a manifesto that you want to stand on in an election. In countries where most of you are from, if a politician wants to interfere with decisions about fertility, he or she gets quickly booted out of office, right? The Chinese government regularly claims that its one-child policy is its major contribution to international climate policy, which is complete nonsense, right? Because the one-child policy was introduced for completely different reasons long before we started worrying about climate change. But they often make this claim. The second, and there's of course other populations that actively reduce the population, like Sudan and Zimbabwe, but that's not the sort of thing that you would want to do necessarily. The next thing you can do is reduce economic growth. Very effective. What you're looking at here is the GDP of the former Soviet Union, which at one point collapsed when you guys were very young. Oh, were you even born? You were born, right? No. So that's the blue line, and took CO2 with it, right? So this is very effective as a policy, but again, not necessarily a platform you want to stand your election on, right? And that means that you essentially have 2 options only. If you don't want to touch population and you don't want to touch economic growth, then you have to improve energy intensity, or you have to improve carbon intensity. And not just that, but you have to increase your improvements in energy and carbon intensity so much that they overcome economic growth, right? If you want your emissions to fall, well, your economy is growing by 3% per year. That means that your carbon and energy intensity have to improve by more than 3% per year, right? So it's not enough to just improve things. No, they have to improve at a particularly rapid change. Saving energy. There's a lot of things that go on through the market. I showed you this thing. And what we've seen is that from the 70s onwards, we actually see a market improvement in energy efficiency. Bill Nordhaus has a fabulous paper that actually takes this back to Babylonian times for lightning. And we see that as far as we know, energy intensity has improved, energy efficiency has gone up for as long as we know. The reason for that is very simple. Energy is a cost. And if you can reduce the energy use of a particular gadget, then that's a good thing, right? So if you're a manufacturer of, say, fridges, and you can make the exact same fridge as your competitor, so the same color and the same size and the same contents and the same cooling and what have you, but yours uses 10% less electricity to run, and it sells better, right? Because it's cheaper to run for the people that buy it. Simple as that, right? If there is a good reason, if you're making things or if you're using things to save on energy, because it's a cost, right? And that explains why this trend is there. Now that is true for every single product, that if you look at a product and you compare like with like, then they become more and more energy efficient over time. But that does not mean that overall energy efficiency falls. There is of course the rebound effect, or the Jevons effect. That is, if you improve the energy efficiency of something, then it becomes cheaper to use, and therefore people use it more, right? If you have a more efficient car, then you want to take the family for a Sunday drive, and it's not as expensive, so you're more inclined to do it if you're budget constrained and you like driving. But there's another thing that is going on that is best illustrated with these graphs. What you're looking at is slightly older data of the fuel economy of cars in the US. That's the top blue line that you see, and what you see is that it's been flat. And I just told you that for every single product things get better all the time, but here it is clearly flat, and this is fuel economy, so this is the reverse of energy efficiency. But what has happened at the same time in the US, and that's the two other graphs that you're looking at, the weight of the cars has gone up over the same period, and quite considerably so. And you think you may have seen big cars on the Dutch roads, right? And you think you may have seen cars on television that seem biggish. You go to the US, God, they're big, right? These cars are enormous, right? And that is what you see in the weight. And of course, if your car gets bigger and heavier, but you want the same performance, then you need to put in a more powerful engine, right? And that's the very bottom graph. You see the horsepower of the engine has gone up quite considerably as well. And at the same time, the fuel economy has been flat. So this is a remarkable feat of engineering, right? You drag more and more weight around with more and more powerful engines without burning more fuel. But of course, you're still burning as much fuel as you used to, so your CO2 emissions have not come down, right? And what has happened here is that people use the technological progress not to reduce their energy use, but to increase comfort, to increase a feeling of safety. Those bigger cars are not necessarily safer, perhaps to increase bragging rights and those sort of things. But they did not use the technological progress to reduce emissions, right? Continuing on saving energy, if you ask an engineer, then he or she will tell you that 30% of all energy serves no useful purpose. If you look at what people do, they want a cup of tea and they boil an entire kettle of water. You walk around the university after dark, there's a lot of lights burning, but there's nobody in the room, right? So a lot of energy serves no useful purpose. And that would suggest that it's relatively easy to change these things. But some of it is just force of habit, and you need a fairly heavy-handed intervention to change habits, and that may be counterproductive, right? Most of you probably share an apartment with other people, and you may live with an energy Nazi, right, who just keeps saying that yes, you have to turn off the light in the bathroom if you're no longer there. And yes, you're completely wasting energy, but you can create very unpleasant social situations, right, through this. So it's not costless to change these things. But if you're talking about the energy use after dark at a university, lights burning in rooms where there's nobody there, we're actually talking about a principal agent problem, right? Because I, the lecturer, am responsible for turning off the lights. But I don't pay the electricity bill, right? The rector pays the electricity bill. It goes to the central billing. My salary doesn't go up if I turn up the lights. My research budget doesn't go up if I turn up the lights. It's nothing to do with me. I am the agent. I control the resource. But the rector pays the bills. He is the principal. And if those people are not the same, then you can get into these situations of a waste of energy. And that is not just for relatively trivial things such as electricity use in lecture halls. There is a solution for this, right? And the solution would be that every time I walk into a lecture hall, I need to swipe my ID, and then whatever electricity is used goes to my personal account, right? That's the solution here. But you can sort of like see the administrative cost. And if you know the unions, you would know that it would be up in arms if you were to suggest that, right? But it also goes for, and these sort of problems also hold, say, in the housing market. Presumably most of you guys rent, and that means that you are paying the energy bills, but in your lease it says that you cannot change the physical properties of your apartment or the room, right? So if it is not double glazed or badly insulated, you cannot do anything about it, but you suffer the consequences. And at the same time, your landlord or landlady, they have the right to do it, but no immediate reason because they don't pay the energy bills. And the information in the rental market is such that its true energy costs of running this particular apartment or this particular house do not get fully reflected in the rental price, right? So the landlord can invest in double glazing or better insulation or a smarter heating system, but cannot recoup that cost through higher rents, right? And there, of course, we're talking about much greater energy bills than the lighting in this particular lecture hall, right? And another thing you can do, of course, is convince people to use less energy, which is very difficult, right? You can convince a select few that perhaps a holiday in Brighton is just as good as a holiday in Bangkok. Brighton is really a lovely city, you should come visit, right? But it's not a convincing argument to most people. And then you can switch energy. Fossil fuels are not created equal. Gas has about half the CO2 per joule as coal, and that explains the trend that you see here. So we're looking here at CO2 from an energy use in US power generation over a 13-year period. And what you see is that not a whole lot has changed in terms of total electricity use. Has gone up a little bit from say 37 billion, from 3.7 billion megawatt hours to 4.1 billion megawatt hours. But you see a remarkable change perhaps in the composition, right? You see that the brown bits have shrunk and the red bits have grown. That is a substitution from coal to gas. And then in the black line, what you're looking at is the CO2 that is generated by the US electricity system. and that has fallen reasonably from around 2200 to around 2000. So that's a 10% emission reduction over a decade, right? And that is all because of the switch from coal to gas. That's not, if you look at the very top, not because of an expansion in renewables, the blue line, or the green line. Blue is hydro, green is wind and solar. No, this is switching from coal to gas, which is actually a very powerful way of reducing greenhouse gas emissions. Now, if I were to put up the same graph for Europe, we would see the opposite. The reason that it happened in the US is because they discovered how to frack gas, and that meant that the price of gas plummeted and people simply switched. They gave up burning coal and instead burning gas instead because that was a cheaper thing to do. Problem with that is then you have a surplus of coal, and a lot of that coal ended up in Europe, and in Europe the relative prices move the opposite direction. So in Europe coal has become cheaper relative to gas, and in Europe you would see the opposite. And this has to do with World War II, where the US sort of decided that at that time it made sense to ban the export of natural gas, and that has been on the books ever since, and that is why they were exporting coal rather than gas, right? And that is why in Europe it's the other way around. So what can you do? You can switch from coal to gas, and then you can switch to other more carbon poor sources. And there's a whole range of technologies out there that you can use. And there's two mature technologies out there that are essentially carbon free. That is nuclear and hydro. And even though these are proven technology, they also have proven to be very problematic technologies. Nuclear is extremely unpopular still, and a lot of people are scared of it to death and will do a whole lot to protest and make sure that it doesn't expand, right? Or shut down existing nuclear power plants. The same is true for hydro. If you want to build a large hydro dam, you need a large reservoir, and that means that you need to displace lots of people and flood lots of land, right? So these are proven technologies, depending on who you believe, maybe relatively cheap technologies in pure economics, but simply there seems to be very little social support for this, at least in Europe and North America and Japan. If you really want to make a dent in CO2 emissions with nuclear, you have to expand nuclear power production into basically every country on the planet, right? And then you create proliferation problems, because if you can run a nuclear power plant, then you can also make a dirty bomb, and if you're clever enough, you can also make an atomic warhead, right? So there's proliferation issues. And there's one thing about building up a nuclear power industry in China, which is a relatively organized society. If you really want to make a dent in CO2 emissions, then you need nuclear power plants in the Central African Republic, and so on and so forth, right? Chances are they won't be safe. Now, the next two things shows that this class is old, right? So what people have been going for are wind and solar, and yeah, it says here that wind and solar are expensive. They used to be expensive. At the moment, they are getting close to grid parity. That is, they become almost competitive without subsidies. So at the moment, wind and solar still need subsidies, but what we see in the offshore market at the moment is that people are bidding for 4 cents a kilowatt hour offshore in 10 years' time. That's cheaper than gas. And what we've also seen, and that was actually already last year, is that people are bidding for solar, concentrated solar power, not photovoltaics, at 3 cents a kilowatt hour. I mean, coal and gas are 4 to 6 cents per kilowatt hour. If you can make solar at 3 cents per kilowatt hour in the Moroccan desert, where land is cheap and the sun is strong, right? Then, so these things are taking over. That does not mean that there are no problems with this, right? Wind and solar are not dispatchable. They're unpredictable. So photovoltaics, if the sun goes down and you want to turn on the light, but your photovoltaics don't work when the sun is not shining, right? So that is a problem. The wind sometimes blows hard and sometimes doesn't, particularly in Western Europe. What we have is that very cold periods where you want to use lots of energy are also the periods that are basically wind still, right? So there are issues there with predictability and dispatchability and intermittency. In the UK, we can't build wind turbines on land anymore because everybody hates the sight of them, right? So there's those issues. Now moving into sea. A problem that hasn't really emerged with solar but will is that these photovoltaic panels are full of nasty chemicals and heavy metals. And that's fine as long as they're on your roof, but they won't stay on your roof forever, right? At one point they will have to be discarded, and they are essentially chemical waste, right? So we're creating an enormous waste problem in the future that hasn't quite emerged because we haven't been taking them down yet, because they're still useful up there. Another problem with wind and solar is that the main sources are far away from where the people are. The big winds are at the Atlantic seaboard. We live further inland. The big sun is in the Saharan desert. That's not where a lot of people live, so you need transport, you need storage, and at the moment they're not particularly good for transport, for using cars and trucks and that sort of thing. That is changing, but at the moment an electric vehicle is nice if you live in the city as a second-hand car, and if you have lots of money then an electric vehicle is nice, but it's not much use otherwise. So people have been looking at climate-friendly transport fuels, and the most promising one there is biomass, and there's 3 generations of biomass. The first generation is the stuff that we're currently doing, and essentially what we do there is use very old technology. We take seeds, rapeseed for instance, we press it and we have oil, right? The Romans knew how to do that. It was very old technology. The big problem with the first generation of biomass and biofuels is that the stuff that we turn into fuels are stuff that we can eat or that pigs can eat, right? So you have a direct competition with food production. And at the moment 25%, 30% of the US corn production is diverted to ethanol, and that has driven up the price of tortillas in Mexico, right? Including leading to some riots there. So there's direct competition with the food production, so you can do this at a relatively small scale, but you can't upscale it, right? Because we have more and more mouths to feed. If there's a first generation, there must also be a second generation, right? And that is essentially a smarter processing of the biofuels. So what is coal, or what is oil? It's essentially plant material, right? It's very old plant material that Mother Nature very kindly over the last couple of million years has dried for us and pressed for us and sort of condensed into this nice lump of coal that has a very high energy density. Now what is biomass? That's also plant material, but recent plant material. So you have a field full of, say, corn stover, and you need to harvest it, and you need to dry it, and then you need to compress it, and then you need to transport it, and so on and so forth, right? So that is inherently expensive. And the second generation of biofuels people are making that whole process smarter and cheaper, right? But you still, essentially, Mother Nature has done this with fossil fuels for you for free, but with biofuels you have to do it yourself, right? So the second generation will improve things but may not necessarily solve things. But there's also a third generation, and that, I think, is best illustrated in this particular picture. So what you're looking at the top is the original brassica plant, right, which is essentially a mustard plant. And through selective breeding, this has been turned into your carrots, your Brussels sprouts, your kohlrabi, your kale, your broccoli, your cauliflower. They are all the same plant, right? And what we have done over the last few thousand years through selective breeding is take plants that are natural and maximize them for food use, right? And we have been quite drastically successful in that, and plants have completely changed. What we have not done over the last few thousand years is optimize our plants for fuel. We're basically still chopping up wood and chucking it on the fire, right? And what people are now starting to do is optimize plants for fuel. We've only just started, only 15 years ago, 15 years or so. But of course we know much more about selective breeding than our ancestors did, who picked up the wild mustard and started turning it into Brussels sprouts, right? We know this much better than they did. And of course we can genetically engineer things that they could not do, which suggests that there is an enormous potential for improvement in the biofuels. Promising things happening in the lab. Unfortunately, it has not been working in the factory, but they now have algae that essentially you put them in a vat of water, you come back 2 days later and there's a film of diesel floating on top of your vat of water. You just scoop it up and stick it in your car. That can be done now in the lab, right? And it's a matter of time before this is upscaled to commercial applications. So great potential there, but perhaps too early now. What will it all cost? So what you got from what I just told you, this problem is solvable, right? We can reduce our greenhouse gases, but it will come at a cost. None of the things that I've just talked about come for free, right? None of these problems are insurmountable, but it will come at a cost. So that is, if you just look at the options, there is an alternative way of looking at this. At the moment, there's no climate policy, and that means that you can dump your CO2 in the atmosphere for free. There's no constraints on that, there's no cost associated with that. And with climate policy, either they're putting a constraint on what you can do, or they make it costly for you to do it. And then necessarily your situation is deteriorated, right? There's necessarily a cost to that. Or you can think of this mathematically. You will first have an optimization problem without climate policy, and now you have another optimization problem where all of a sudden you have this constraint to your CO2 emissions. And if you paid attention to your Lagrange optimization, as soon as you put a binding constraint on a system, then you necessarily incur a cost, right? The question is, what is that cost? And the answer is in this table. And you can't read the table, and that is on purpose, because the numbers are not that important. So what you're looking at in this table, if you move from left to right, is you see ever more stringent climate policy, and if you move from top to bottom, you see alternative assessments of the cost. And if the first thing you notice, if you look at the alternative assessment here now graphically and in blue so that you can read them, is that these different assessments disagree on what it would cost to do something about climate. And they don't, this is the cost and the margin, so this is the carbon tax you should impose. And if you want to stabilize CO2 concentrations at 550 parts per million, that's roughly 3 degrees of warming. Then some models say, well, you should impose a carbon tax of $1 per ton of carbon, and other models say you should impose a carbon tax of $20 per ton of carbon. So that's a factor 20 difference, right? And that's quite a range, right? That's quite some uncertainty about what it would cost to reduce emissions. And I'll come back to the reasons in a few minutes. But the basic reason is simple. This is an assessment of future climate policy, right? And the future is uncertain, so you should not expect a narrow range. But I'll get back to why these models differ in a second. The other thing you may wonder about is what do we actually mean by climate policy, right? And sometimes journalists ask me what would climate policy cost, or a politician would ask that question, and that's just a very silly question, right? It is as if they think there is such a thing as climate policy, but that's of course not true. There's all sorts of things that are going on, and that is illustrated in this graph here. So if we move from left to right, the carbon tax needed goes from 10 to 550, and that is the stringency of climate policy. So this should not surprise you. The more stringent a climate policy is, the more it will cost, right? But there's other things going on. In blue, you're looking at the carbon tax that you would need to impose, or the marginal cost, if you have a target in the very long run, and you don't really care how you get there. And then actually what you would do is you would overshoot your target and approach it from above. You may say, well, but that's cheating, right? You have a target for concentration, say of 550 in the very long run, and that means that in the meantime we also want to stay below 550, right? So if you impose that condition, that you have to approach the target from below, then you need to add the red bars to the blue bars, then you immediately see that this makes a difference, right? And for very stringent climate policy, climate targets, it actually doubles the cost of the margin, right? So you can't answer the question what would climate policy cost without providing a lot of detail. Now, this is the carbon tax you would impose if your climate policy applies to the world as a whole. If instead you say, well, it's actually rich countries that emitted most CO2 in the past, and poor countries are poor and they cannot afford this, and instead you say, well, we're going to impose this policy, and this is a slightly older study, we're going to impose this policy around the year 2020, that's next year, for the rich countries, and then middle income countries like India and China will follow in 2030, and really poor countries in Africa and places will follow in 2050, but we maintain the same target. Then you need to add the green bars, and you go from 200 to 550, right? And again, the reason for this is simple. You have a collective target, and if you're all working towards that target, then it's relatively cheap. But if more than half is sort of exempted from this for the initial bit, that means that the rest has to work much harder, right? That follows quite trivially. So you can't answer the question what would climate policy cost without actually adding a whole lot of specifics to this. Now these numbers don't mean anything to you, right? dollars per ton of CO2. Let's assume that a dollar is roughly equal to a euro ton of C. The current price of CO2 in Europe is around 20 euros per ton of CO2, which is roughly equal to 80, perhaps 90. No, it's more like $90 per ton of C, right? The price in Europe is roughly here at the moment, which immediately suggests that if we want to go for 450 parts per million, then we need to first raise the price in Europe at quite an amount, and then also convince the United States to follow suit, right? And then in 10 years' time, Canada and India should adopt the same price. Now you also don't know what 450 means, right? 450 means that you have a 50-50 chance of hitting the upper target of the Paris Agreement of 2 degrees. And if you want to go for 100% or a 90% probability of doing so, or want to hit the lower target of Paris, 1.5 degrees, then you don't just need to convince the US to adopt double the European price, right? You need to do much, much more than that. But it tells you something about the feasibility. So now, why do these abatement costs differ so much between models and between assessments? And there's actually a whole range of reasons for that. The first is the availability of technology. If you assume that there's no social constraints on the expansion of hydropower and nuclear power, then it is relatively cheap to reduce emissions. But if you assume that those constraints do exist, then it becomes a lot harder. If you assume that nuclear fusion will become available commercially in a relatively short period, then it's much cheaper to reduce emissions than not. The problem with nuclear fusion is that for 50 years they've been saying we're going to do this in the next few decades, right? And they keep on saying that, and they're just making the same promise. We'll have cracked this problem in 20 years, and they've been saying that for 60 years now. We will have cracked this problem in 20 years. The next thing that goes in there is essentially the relative price of renewable energy to fossil energy. Now you may think, well, we'll just look that up, right? Because these things are traded in the markets. It's actually not true. A lot of these things are actually commercial secrets, so it's very hard to discover what people actually pay for their electricity and actually pay for their fuel. If you're talking about commercial contracts. And that means that different agencies and different academics have just different estimates of how much wind really costs and how much photovoltaics really cost. That is true for today. It's of course even more true for the future, because most of these models are about the future. So what matters there is what is the price of oil in the year 2030, what is the price of solar in the year 2030, or rather what is the ratio of the two, right? And reasonable people can reasonably disagree on these projections. The next thing that you need to worry about is how does the economy respond, say if we put on a carbon tax. Essentially what you're asking for is what is the price elasticity of energy, and what is the substitution elasticity between different sources of energy. And again, you may sort of argue, yeah, but that's well known, right? No, that's actually not well known, because we very rarely have the data to estimate these things accurately. And and different estimators and different data sets would actually give you widely different results, and people may have been following different guidance there. The next thing there is about the responsiveness of the economy, is how much of these emissions can actually respond and how much is set in stone, right? So if you look at the energy use of this particular building, that is driven by the physical characteristics of this building. And the only way to fundamentally change that is to tear it all down and build a new tower, right? Now, I've been at this university for a long time, and this tower has always been there, as has always been the discussion that we're going to tear it down and build something proper, right? And different people may disagree on the exact lifetime of these things, and the same is true for machinery and so on and so forth. The final point I want to make, I'm going to talk about tomorrow morning. Okay? I see you guys then.